we're going to go through 4 example problems together on how to convert a set of equations into state space form, and then also conduct a step response. This might be our u value, and that's our y, our response. So we want to be able to calculate numerically what this is going to do for a unit input change of the input on the output. And we'll do that in Python with the signal package, and I'll just demonstrate some of the syntax there for working with these linear time invariant systems. So let's do this first one right here. We have this single differential equation and a single output equation, and in our state space form we typically have number of inputs u, we'll just call that m, number of states, I'll call that n, and then number of outputs, we'll have that be dimension p. So when you're talking about the dimensions of these matrices, that this is going to be an n by 1 matrix, just a column vector with entries like this. So this is an n by 1. U is going to be an m by 1. Okay, and then we have y is going to be a p by 1. So just to make the the dimensions work out, and also dx dt is also going to be an n by 1. So a matrix has got to be an n by n. The inner dimensions need to agree, and then the outer dimensions of that become the result. Right there, need to be consistent with that result on the left-hand side of the equation. And so likewise, this is going to be an n by m matrix, okay, where those inner dimensions agree, and then the outer dimensions are n by 1. And so let's go down here as well. We have n by 1 for x, and then an m by 1 for u. So d has got to be a p by m. Okay, inner dimensions agree. The result is going to be a p by 1 vector. And then also for the c, we have a p by n. So in this case, we have just one input, we have one state, and we have one output. So all of our matrices are going to be just a single value. So let's go ahead and just convert this, and the way we do that is divide, isolate this on the left-hand side. So I'm going to put this on the right side, and then also divide by 3 everywhere, and that's going to give me dx dt equals negative 4x plus 6u, and then we have y equals 1 times x plus 0 times u. So here are the matrices right here, actually just single values, b, c, and d. And so let's go over to Python now and just go ahead and plug these in. I'll just go ahead and move this over to the side here, just so we can see the values as we type these in. And I'll move this up here. Okay, there we go. So the first thing that we're going to need, I typically just do as a first thing, import numpy as np, and then from scipy we're going to import the signal package. So those are the first 2 things that we're going to need to import. So for problem 1, and we'll go through a few more of these as well, we're going to have a is going to be equal to negative 4, b is going to be equal to I put 6 there, that should have been 2. 2u, okay. This should be 2, and then c is equal to 1, and d is equal to 0. And then to put this into a linear time invariant signal form, we just do state space, signal.state space, and then we have our A, B, C, and D. And then to simulate this, we just do T1, Y1 is going to be equal to signal.step, and then we have our sys1 there. Okay, I'm also going to put in here, just to be able to plot this, I'll do matplotlib inline. I'll just be for Jupyter if you're using Jupyter. If you're using an IPython, to be able to have it show up within the browser, and then we'll do import matplotlib.pyplot as plt. Okay, so we want to be able to see this plot here, and so I'll just do plot t1 y1. Okay, let's see, I've got an error here. Oh, I haven't run this one yet. I'm going to run that one first, and then I'll run this one with the PLT in there. Okay, so here's our step response. You can see, I had a, let's see, so here is about my, I can't write on this one. Okay, so anyway, I have a gain of 0.5 and a time constant of about 0.3 or so. Okay, so there's my step response. Okay, let's go on to the next problem now. Over here, I'll go ahead and move this one over. Okay, we'll come back to that Python in just a bit. Actually, I'll just go all the way over. Okay, so here are two differential equations now, and we want to fit this into state space form. Now this one is going to be, this one has dimensions. First of all, u is going to be just dimension 1, and then x is going to be dimension 2, okay, vector of length 2, and then y, we still have just one output. So let's go ahead and write out our state space form here just to see what we're expecting. Okay, plus du. And if I write it out into matrix form, I have, okay, and then 2 by 2 right here, that's going to be n by n. And then I have x1, x2 plus, and then this is going to be an n by 1. Okay, so I'm going to have two values right there times my u, and then I have my y is going to be a p by n, and so this is going to be a 1 by 2. So I'm going to have 2 values right there times x1 and x2 plus just a single value there times u. Okay, so there's my state space form, and now I need to fit these equations right here into that form. I'm just going to take this first equation right here, and this is going to be my first row right here in that matrix form. So I'll divide this by 2, okay, and bring this one over to this side of the equation, and that'll be 3, and that'll be 4. And then in this form, this is going to be -3. I don't have an x2 there, so I'll just put 0. And then this is going to be 4 right there. And let me do the same thing on this side. I'll divide by 3. Okay, and then move these over to the other side. And so that's going to be a -2 and -3. And there's no input, so that's going to be 0 for the u. Now this is the average of the two states, x1 and x2, is going to be our output. So let's say I had two temperatures that I was measuring, and I was going to take the average of those, and that would be my measured output for my system. Then this is going to just be 0.5, 0.5, and then 0 there for u. Okay, so I have my state space form here. Let me go ahead and just go back to the okay, back here, and let's go ahead and just simulate this one as well. So I had let's go ahead and create a new cell down below. Okay, so I have A is going to be equal to, now if you want to do a matrix in Python with different rows, you're just going to have these square brackets separated by a comma. So I'll have -3 and comma 0, and then -2 comma -3. There's my A matrix. My B matrix is going to be two rows, one column, and so I'll have 4 and then 0, and then my C is going to be just 0.5. This is just going to be a row vector, and then D is going to be equal to 0. So let's go ahead and put this into state space form again. I'll just go ahead and copy these two. Actually, I'll copy these 3 and just change it to the next one, which will be sys2, t2, y2, and let me just change that to system2 here. Okay, so let's go ahead and just compute this. Looks like that one isn't quite right. I did something, you know what, 4, 0, let me just check this, see what I did in here. Okay, it may be because I had these as non-floating point numbers. I don't think that's the case though. Something I can check first of all. If you're using a Python 2 division, you got to watch out for some of these things that, division by integer values. Okay, it looks like that was the case. Okay, so here's here is the step response right here. I had this A, B, C, D matrix, and then I had I just calculated a step response here. Okay, let's go on to the next one now. Let's go on to a third example. This one's just a little bit more difficult. We have a second order differential equation here, and we need to put it into state space form. So with if you have higher order derivatives, you can always break that down into multiple first order differential equations by just defining some new variables. So I'll just, every order of differential that you have, in this case we have a second order, we need an additional state to be able to track that. So we have, let's just say x1 is equal to y, and then we'll say that x2 is going to be equal to dy dt, and then we'll have dx2 dt is going to be our second derivative of y. So these are the things that we're going to substitute into this equation to give us two differential equations that can be put into state space form. So again, in this case we have u is going to be dimension 1, x is going to be dimension 2, and y is going to be dimension 1. So we're going to have x1 dot x2 dot equals, and then we need to find the entries again that are going to go here, 2 by 2 matrix, and then we're going to have a 2 by 1 times our u value, and then we'll have y. Okay, and our C matrix there with just a single value. This one is almost always 0. Right here we rarely measure the input. We assume that we know the input and are commanding that, but we don't necessarily need that term. Some researchers, some publications, they just leave this term completely out. But we'll just leave that in there. Okay, so let's go through this one, just making the substitutions. Okay, we have And one other thing to substitute, our first equation is just going to be this one right here, where we have x2 equals dx1 dt. So we need these in terms of x's. We need to eliminate the y's. And then let's go ahead and start making a substitution here as well from this equation. We have 4, and then this is going to be times dx2 dt. And we can only have one differential term in each unless we do the more general form of state space, put like an E matrix there, and then we can have multiple differentials in our equations. But let's just keep going with this. So I have to do 2 times and then dy dt. I could either use dx dt, dx1 dt, or I could use x2. So because we already have a differential there, let's just go ahead and do x2 there instead, and then plus x1 equals 3 times u. So we just need to have this on the left-hand side of the equation. So we'll divide through by 4 everywhere. Okay, and then put these terms on the right-hand side of the equation by subtracting those quantities from both sides of the equation. So we have dx2 dt equals, and then I'll put negative 0.25 times x1 minus 0.5 times x2 plus 0.75 times u. And let's do our first equation as well. dx1 dt equals 0 times x1 plus 1 times x2 plus 0 times u. So we just want to fit these into state space form now. So this is going to be 0, 1, 0, and then negative 0.25, negative 0.5, and 0.75. Okay, let's go back and simulate this one as well. So I'm just going to take this this example right here and copy it. Hit Alt-Enter to get a, okay, and paste that in. I'll change this to System 3. This is going to be our third one that we're going through. And let's see, the commands are going to be the same. And for this one, let's also do just a little bit of analysis on the A matrix. We want to see if this one's going to be, the system is going to be stable or not before we actually even do the step response. So one way to do that is to just print the eigenvalues of the A matrix. And if all the eigenvalues have negative real parts, then we know the system is going to be stable. It's going to be whatever initial condition you give it, it's going to exponentially decay to a stable point. So to do that, we'll just use the a NumPy linear algebra, and we'll use the eigenvalue package there. We'll do the eigenvalue of A, and we just want the eigenvalues. We don't want the eigenvectors as well, so we just want the first thing that comes out of that. So I'll put the bracket 0 there. And so we'll be able to see if this is going to be stable even before we do the step response model. Let me just change some of these. 0, and then we had, let me move this over just a little bit so we can see it. Okay, 0.75, and then up here we had 0 and 1, and then negative 0.25, negative 0.5. Okay, and then let's get back down here to the y. Oh yes, I forgot the this one as well right here, and that one we're just going to use this equation. So that's just going to be a 1 and a 0. If you multiply that out, it's just y equals x1. Okay, going back, let's go 1 and 0. Okay. So here we have it, and let's just scroll down so we can see from these these eigenvalues, we have an imaginary part, but we also have a real part. Now both of the real parts are negative 0.25, and so that means that the system is going to be stable. So let's go down and look at the step response. So we did have an underdamped system with a bit of overshoot, and you can see the response. It is oscillating, but it is stable. Okay, let's go down to the next one. Okay, let's go down to this one right here. These are nonlinear differential equations, and so the first thing that we need to do, there is a state space. When you talk about state space, you put it into a nonlinear form as well. The nonlinear state space form would just be something like this. F1 as a function of x1, x2, and then also u, and then we have x dx2 dt is going to be our second function, and that's going to maybe be a function of each of those as well. And then we have our output equation. I'll just go ahead and write this. We're going to have times x1, x2, and just because we're writing this out, I'll write the y1 and y2 there. Okay, and then we have d as well. Okay, there's going to be two values there. Those are going to be zeros. Now this output equation, I'll just do this one first because it's probably the easiest to get out of the way. To do this one, the first equation is y1 equals 0 times x1 plus 1 times x2. And then the second equation is y2 equals, and then it's going to be 1 times x1 and 0 times x2. Okay, so we've taken care of our C and our D matrices there. But now we need to come up with our A and B, and one way to do that, let me go ahead and just bring up this content here that's also available. And again, if you want to go back and get the source code for this, or a little bit more on state space, you can come to this website right here, and then in the bottom right just hit state space, and it'll bring you to this page that talks about state space modeling with a couple examples. And we're going to be doing the general nonlinear system, so what we need to do first of all is just linearize. And so we're going to be, in this case, here's our formula for linearization, and I'll go ahead and paste this over here as well so we can see it. Okay, so what we're doing with any general nonlinear equations, we just take the partial of that function with respect to each variable, and then these become coefficients. So these will become like alpha 1, 1, alpha 1, 2. Okay, and these, in this case I showed 3 inputs, but in our case we only have, 1 input, so this would go away. We just have these 2 terms and these terms right here. Okay, so we have, this is going to be our formula for creating these state space models out of a nonlinear expression. So to do this, let's just fit this into our standard form first of all, the nonlinear state space form, and then we'll linearize it. So this is going to be negative 0.5 x1 squared minus, and then we're going to have 3/2 x2 squared plus 16 divided by 2, which is 8 times u. Okay, there's our first equation with just the differential term on the left hand side. And then the second equation is going to be here, negative 2x2. Okay, so there's our second equation. So we want to use, just take the partial of each function. So this is going to be f1 of x1, x2, and u. And this is going to be f2 of x1, x2, and u. There's no u there. Okay, so let's just build our state space model now. Okay, I'll just have so we can fill in the blanks here. We just have 4 values. Okay, and then plus, I'll fill in 2 values here for those. Okay, I'm going to make this just a little bit smaller. Okay, so let's just take the partial of this one with respect to x1. And so this is our only term with x1 in it, so it's just going to be negative x1. That's our partial of f1 with respect to x1. And then we'll plug in our nominal conditions. And our nominal conditions in this case were listed right here, where u nominal is equal to 1 and x nominal is equal to 2 for both x1 and x2. Okay, so we just plug in 2 right there. So this first term is going to be equal to negative 2. And the next one, so let's do the partial with respect to x2. And that's going to be equal to negative 3x2. And so we also plug in our nominal condition of 2 there, and that's going to be negative 6. Okay, so you can just take the partials here. I'm going to do the next one. This is going to be negative 4x1 nominal and negative 4x2 nominal. So these are both equal to negative 8. And then let's do it with respect to u as well. And so this is going to be equal to, on this side, it's going to be equal to 8 and then 0. We don't have that term there. So here's our state space form right here. And then we knew that our C matrix was 0, 1, 1, 0 times x plus 0 times u. Actually, that's going to be 0, 0 times u. Okay, so let's put this into our this form and then be able to simulate this. Alright, and I'm going to go ahead and copy this one as, again, it's similar dimensions, but we'll just augment it a little bit. And then we also want to do our stability analysis as well. Okay, paste that in, and then let's just go ahead and start changing some of these values. We have negative 2 and negative 6 and negative 8 and negative 8. Okay, don't forget the decimal points there. Apparently that causes things to not work very well if you don't have the decimals there, because they are integer versus floating point numbers. And then in the B matrix, we just had 8 and 0. Okay, C, we've got to give ourselves an extra row here. Just go ahead and do that for an extra row. And this is going to be 0, 1, and then 1, 0. Okay, D has got to be just 2 rows, both equal to 0. And this is going to be our fourth one. Okay, and there we go. There's our fourth. And so we'll go ahead and compute this. And so we see, first of all, our eigenvalues give us something, that might alarm us. We have a positive eigenvalue equal to 2.55, and also a negative one as well. So it only takes one positive eigenvalue to make this system unstable. So we think, without even looking at the plot, the system is going to be unstable. In fact, there is the response. We have 2 states that came out of it, 2 outputs, 2 measurements, and so there they are. It's unstable. It goes to it's going to exponentially deviate from the starting point. Okay, I just want to show one other thing with these. You can use the step function, but let's say you have just some arbitrary inputs that you would like to be able to simulate for this, and so we're going to use the LSIM in the linear simulation instead of the step. And for that, we just need two additional inputs. We need U, and then we need T. And so our time, where we want the simulation for each of those points, we're going to use maybe something like NumPy linspace, and we'll go from 0 to, in this case, let's see, where do we want to go? I'll do 100 points, and we'll go up to about 100, okay? So we'll go up to 100, and we'll do 100 time steps, or 101 points. And then our U values, let's do ones, the same length as T. Okay, but then at a certain point, maybe at, well, let's go zeros instead. We'll start with zeros. And then from 20, we'll do 10 on, okay, 10 to 50, we'll set that equal to 1. And then from 50 to, and that'll be 10 to 49, actually. And then 50 on, we'll set that equal to 2. So let's go ahead and just plot our TU, and then also we'll plot our, we'll do that with a red line, and then this one with a blue dashed line, just to be able to see the differences between those. Okay, so let's see, too many values to unpack. Oh yes, so one other thing with LSIM is that you also need the states. It also returns the states as well. So I'm just going to have the time and the Y values, the time and the output. Okay, and so there are the there's the two the input and also the output for this linear simulation. So you can give these linear time invariant models, these state space models, any sequence of inputs, and you'll be able to simulate the output with the LSIM command. Okay, so that concludes this. Just to summarize, we went through 4 different problems. The first one was just one state, one input, and one output. So fairly simple. We moved on to a 2-state, one input, one output. And then on to a second order differential. We showed that you have to have the same number of states as you do order of the differential. And then finally you have a nonlinear differential equation that we linearized and put into linear time invariant form, and then simulated that. One other thing to note on this is we were just simulating the deviation variables, but if you want to get back to actual variables on this, just add in those nominal values. So we would just add back in that 2 value. In this case, it isn't going to make a lot of difference here. It's exponential, so you can't really see it. The scale is kind of off. But if you want to get back to the non-deviation variable form, just add back in your nominal conditions there. Okay, that concludes this tutorial on how to use these state space models in Python.